Hello everyone, today I'm going to show you how to calculate any logarithm by hand. We're going to start with an example, which is going to seem very random to you, but don't worry, I'll prove to you why it works at the very end. So the example is to find log base 10 of 2. So we start from letting b1 equals 2, and 10 is between 2 to the power of 3 and 2 to the power of 4. And we're going to say that n1 is 3. Next, we're going to have to find b2, which is just 10 divided by 2 to the power of 3, and is 1.25. Okay, now 2 is between 1.25 to the power of 3 and 1.25 to the power of 4. And we're going to say that n2 is equal to 3. b3 is 2 over 1.25 to the power of 3, which is 1.024. Next, 1.25 is between 1.024 to the power of 9 and 1.024 to the power of 10, which means n3 is equal to 9. Now we can find b4 by calculating 1.25 over 1.024 to the power of 9, which is equal to 1.009741958. Now we can continue forever, but we don't have to. We just have to find a reasonable approximation because the rest just won't matter. And from this, we can just construct a continued fraction. So log base 10 of 2 is equal to this continued fraction right here. Now next, we just have to calculate the convergence, and to do that we just construct this table, and here we go. Now if you haven't seen convergence, don't worry, I'll show you what that is. So if we cut off continued fractions at various stages, we can obtain the convergence at that stage. For example, for this convergence, the first convergence would just be 3, the second convergence would be 3 plus a third, and the third would be 3 plus 1 over 3 plus a third, and so on. Now, this will seem very annoying to calculate, but don't worry, we have something easier. So if we let Ci to be the convergence of the continued fraction a1, a2, a3, at stage I, and let Ci to be equal to pi over qi, so we split the numerator and the denominator, then we have these two recurrence relations, and therefore once we define the minus first and zeroth pi and qi, we can just calculate the ith, p, and q by using this table here, and we will get this. So let's go back to log base 10 of 2. Here is the continued fraction, and here's what it is when you Google it. Now we can see that the second convergence is already pretty accurate, and so is the third. Now let's see what's the sixth convergent. Is pretty much the same. And if you continue to do this for a few more times, you'll get a very accurate answer. However, okay, now I'm going to prove to you why this works. So to solve log base b0 to b1, we need to compute two sequences, b2, b3, b4, and n1, n2, n3, we define bi plus 1 to be equal to bi minus 1 over bi to the power of ni, and ni satisfy the inequality, bi to the power of ni is less than bi minus 1 and is less than bi to the power of ni plus 1. So we begin by finding n1. So b0 is between b1 to the power of n1 and b1 to the power of n1 plus 1. And we find b2 to be b0 over b1 to the power of n1. So we can say that b0 is equal to b1 to the power of n1 plus 1 over x1, where 1 over x1 is just some positive decimal. And hence we can say that b2 is equal to b1 to the power of 1 over x1, or b1 is equal to b2 to the power of x1. So next we're going to say that b1 is between b2 to the power of n2 and b2 to the power of n2 plus 1. So we can say that b1 equals b2 to the power of n2 plus 1 over x2, where 1 over x2 is just some other decimal. And since we already know that b1 equals b2 to the power of x1, this means that x1 must be equal to n2 plus 1 over x2. And we know that b0 is equal to b1 to the power of n1 plus 1 over x1, and therefore b0 is equal to 1 over n1 plus 1 over n2 plus 1 over x2. So we can continue this process forever, and we'll eventually end up with b1 equals b0 to the power of this continued fraction. So if we log both sides, we'll get log base b0 of b1 equals 1 over this chunk of stuff. And hence, by calculating more convergence, we can get better approximations of this logarithm. So thank you for watching. I know it will be very hard to calculate logarithms by hand, but this is still very useful. It's often used in computers. It's probably how your calculator actually calculates these conversions. This was first introduced by Shanks, so it's also called Shanks algorithm. He has many algorithms, but it's the one using continued fraction. I can link the journal to you guys. Thank you for watching. Bye.